Hi there. Today's video we're going to finish up chapter 7 and talk about some improper integrals. This is the last section before the exam. And one thing to keep in mind is that it uses a lot of techniques from other sections that we've studied so far. So if you haven't looked at L'Hopital's rule in a while, we're going to use that. We're going to use U substitution. We're going to use integration by parts. Lots of stuff in this section from previous sections. So let's get rolling. So far, an integral as we've defined it is a function defined on a finite interval, and we assumed no infinite discontinuities. Remember, we did allow jump discontinuities, and removable discontinuities are allowed in definite integrals, but infinite discontinuities have not been allowed, and the interval was not allowed to extend to infinity. It had to be a finite interval. So we're going to show how to adjust those two rules in this section. So we extend the concept of a definite integral to the case where the interval is infinite, so in one direction or both. It's called a type 1 integral, type 1 improper integral, and also the case where f has an infinite discontinuity on a closed interval, or it turns out could be an open interval. You're allowed to mix these two together. So type 1 is infinite to the left or right. Type 2 is infinite up or down. So it's easy to remember. Type 1, type 2. Either way, they're called improper integrals, and you'll see why they're called improper when we look how to solve one. So we're going to look at the first type of improper integral, and we're going to look at this region under the curve y equals x squared. We're going to look at this, I guess it's blue region down here. We're going to call it S. It's above the x-axis to the right of x equals 1. And we want to look at the part that lies to the left of the line x equals t. So what's between 1 and t? So that's the integral between 1 and t of 1 over x squared dx. So that's what that means. When you solve this, you get this formula that is a function of t. So that means depending on what t is, it tells us the area. So the integral from 1 to 2 under the curve 1 over x squared is a half, right? Because you just plug 2 in here and you get 1 minus a half, which is a half. And you can plug in t equals 4, and the area under the curve is 3/4. So it works out real nice. And notice that as you move to the right from x equals 1, the area under the curve has to be less than 1. So if you forgot, just go back and look. This area has to be less than 1, right? Because t can't be negative. So this thing can at most be 1. We also observe that the limit, as t goes to infinity, is the limit of this. Well, if you plug in infinity here, this is 0, so you just get 1 minus 0, which is 1. And it turns out when we rewrite the integrals using this rule, this is why they're called improper integrals. So we define the area from 1 to infinity. This is what makes it improper. But what we do is we put a t up there, and we pull the infinity into the front as a limit. This allows us to still do a proper integral, where t is a number, but then we just let t grow as large as it can be. Right? That's what infinity means, right? It means as large as you want. And you can see down here, here's a few examples, right? And that's what a limit is, right? We can plug in any number for t and get as close to 1 as we want. So if we want to get within 0.000001 of 1, there's a t we can find. Well, that's what infinity means, that there's no closest that we can get. Any number we plug in, we can get closer to 1. All right, well, that's the type 1 improper integral. So here's the formal rules. I'm just going to go over them informally. You have to learn them formally, of course. So if we have this integral that exists for every t greater than a, so a is a point that's given, right? So in the previous example, this was 1, but it can be any number. So if you're given, a to infinity, put a t up here, pull the limit to the front, and take the limit as t goes to infinity. And again, the limit has to exist. If the limit doesn't exist, we have a name for that. It's on the next slide. Now, it can go the other way, too. The limit can be in the left side of the integral. It doesn't have to be on the right side. So if this integral exists for every t less than b, then we would just say that the integral from negative infinity to the b, you put t down here, and you take the limit as t goes to negative infinity. So both of these limits have to exist either to the right or to the left. Now there is a special rule that we're going to see on the next slide. If the limits do not exist as real numbers, then this is where we talk about the special name. So the improper integrals in the first two parts we saw in the previous slide, they're called convergent if the limit exists, and divergent if the limit does not exist. So when we talked about limits earlier in the Calc 1, or even during L'Hopital's rule, you could say a limit is infinity if you're talking about a function. But with areas, we don't want to define areas as being infinite. It's okay with numbers, but when we're talking about areas under curves, we just say it diverges. Now, if both of these exist, right? So a to f of x dx for some number a, and then negative infinity to b for some number b, then what we can do is we can define the limit from negative infinity to infinity. You just pick any point in the interval, compute this integral, and add them together. We're going to see one like this later, but just know that this is a rule. This is a really long section. I think I do 6 examples. I don't have time to do every possible type of example, so just remember that this rule exists. If you see negative infinity to infinity, you have to compute these separately and then just add them back together. So you will see the individual techniques for these separately. All right. Determine if the integral is convergent or divergent. If it is convergent, evaluate it. So we have what looks like a fairly normal integral here, except, oh no, it's improper, right? Negative infinity should not be sitting in an integral sign. Now, we just discussed 2 types of integrals, improper integrals, so you need to check that there are no infinite discontinuities on the interval. You're going to see some problems later and on the homework where there will be discontinuities in the interval, and you have to do those separately. So this does have an infinite discontinuity. It has a vertical asymptote, but the vertical asymptote is at x equals 1/2, and that's not in this interval, so this is a type 1 improper integral. You always have to check. And you're going to see a problem later that if you don't check, you'll get the wrong answer. All right, so this is a type 1 improper integral, so we just pull the infinity sign out of the integral sign, put a t there, and then write the limit as t goes to negative infinity. Now, we can do this as a normal integral, right? This is just, it's a u substitution, but you should be able to do that in your head by now. It's just the natural log of 1 minus 2x and then divide by the power, right? Because the chain rule, when you go the other way, will cancel this power. So we go from 0 to t. The limit stays in the front. Go ahead and evaluate the integral, right? So plug in 0 for x, plug in t for x. The 1/2 is out front. Once you've plugged in the values into the integral and it's expanded out, now you can plug in negative infinity. So this is natural log of 1 minus 2 times 0. So this is natural log of 1. Natural log of 1 is 0, so this whole thing goes away. Then we have negative natural log of the absolute value of 1 minus 2 times negative infinity. That just becomes positive infinity. So natural log of infinity is infinity. And then multiply by 1/2. Half of infinity is infinity. But you don't write infinity, you just say divergent. So if you get a real number when you do this whole process, then it converges, or it's convergent, and you write the number down as the area. We don't write infinity as the area under a curve. We just write divergent. So this is techniques you've seen before. Like I said, this is a natural log integral. Pretty basic stuff. You just have to remember to do the limits. Don't worry, these problems get more complicated. We'll see some of those in a bit. All right, so let's just do another one. Is this integral convergent or divergent? If it's convergent, evaluate it. Here, the improper is in the top. So it's the integral from 2 to infinity of e to the minus 4x dx. So this function is continuous everywhere. Remember, we're checking for vertical asymptotes. This doesn't have any. So this is a type 1 improper integral. We know what to do. Pull the infinity out of the integral sign and make it a limit. Put t in place. Perform the integral as normal. This is another u substitution, but you should be able to do this in your head. Right, just divide by the power. Go ahead and plug in t and 2. And before you do the evaluation step, try to imagine what's going to happen. Everything up to this stage is pretty easy to do. But because you don't want to put in infinity as a number, just think through what's going to happen when you do the limit. What's going to happen here? As t gets very, very large, negative 4t gets very, very, well, it's large, but in the negative direction. E to a very large negative number is 0. If this is not immediately clear to you, go back and study chapter 6 again, because you'll see a lot of natural logs, a lot of rational functions, and a lot of e in this section. So this whole thing is going to be 0. Right? You don't actually plug in the infinity, right? You think through what the limit's going to be. If you're not sure, get out your calculator, make a table, and start plugging numbers in and see what happens. So you get negative 1/4 minus e to the minus 8. Simplify it, which is just 1/4 e to the minus 8. Notice that you cannot do these problems on a graphing calculator. You cannot plug in infinity as a right bound. So if you want to check with the numerical solver, what you'd have to do is like find the decimal approximation of this, and then pick a really large number for the right side of the integral, like 1,000,000 or something, and those two numbers will be very, very close. So that's the best you can do. Because we had been using the numerical solver for a lot of the definite integrals in this section, or in previous sections. Okay, so we've seen both of the type 1 improper integrals. One diverged, one converged. But you still have to work through the problems. You never know if one's going to converge or diverge, just looking at it. Now we want to talk about something that happens all the time. And you always want to make sure that while you're working through the integrals, that you're simplifying as you go. You don't want to wait till the end and then push everything together at the end. Because if you do, you would get this next problem wrong. So just looking at the integral, it certainly looks like it's going to be a partial fractions problem. So we're going to factor the denominator. Then we're going to set it up as a partial fractions problem. Again, you want to check the vertical asymptotes. This has 2, one at 1 and negative 4. Neither one are in the interval. So it's still type 1. So you set up the partial fractions problem. You know how to solve partial fractions. Go ahead and solve it. And then you rewrite this integral as this. So I went ahead and replaced the integrand with its corresponding partial fractions version. And I went ahead and replaced the infinity with a t and pulled the limit out front. So this looks like it's a bad problem. It's really not. So these are both very easy use substitutions. There's not even any chain rule or anything. Right, so you get, both of these have a 1/5, so I pulled it to the front. So it's just natural log of v minus 1 minus natural log of v plus 4 from t to 2. Then I go ahead And you think, well, let's plug in t and see what happens. And you saw in the previous problem, or 2 problems ago, that when we plugged in t, this thing diverged, and this thing will diverge. So what we want to do is simplify first, because if you plug in t here and here, you end up with infinity minus infinity. As you recall from L'Hopital's rule, infinity minus infinity is not divergent. We don't know if it's divergent or not. You'd have to use L'Hopital's rule on it. At this stage, we want to avoid L'Hopital's rule. This is already a pretty long problem. So what we're going to do is simplify on the inside like this, right? Use the rules of logs. Now, this will not be L'Hopital's rule because I can bring all of this stuff inside together, and I can actually get rid of the absolute value. Do you guys see why I can get rid of the absolute value here? Right? Any number in this interval that I plug in has to be positive in both of these, right? Because 2 is bigger than 1, and it goes from 2 to t. So if 2 is bigger than 1, every number from 2 to t is bigger than 1. So these are already positive. So I just bring them together and get rid of the absolute value. I also went ahead and simplified. I plugged in 2. 2 minus 1, 2 plus 4 is 1/6. So I went ahead and did the subtraction problem. So I've already evaluated the integral here. Now you might be tempted to plug in infinity and get infinity minus 1 over infinity plus 4. And that must be divergent. But don't do that. Whenever you have limits that tell you to use L'Hopital's rule, it's possible you could get stuck in an infinite loop. In fact, if you use L'Hopital's rule here, you actually get, you might get the wrong answer. So don't do L'Hopital's rule here. Simplify inside here first. To evaluate the end behavior of a rational function, divide the leading term of both the numerator and denominator by the highest power term in the denominator. So we're going to divide everything in here, in both of these, numerator and denominator, by the highest power in the denominator. So we're going to divide everything by t. So this is going to be 1 minus 1 over t, 1 plus 4 over t. We just divide everything through by t. Now when I plug in infinity, I don't even need L'Hopital's rule, right? When I plug in infinity, this becomes 0, this becomes 0. I just get 1 over 1. Well, this is just natural log of 1, which is 0. So I'm just left with 1/5 natural log of 6, and that's the answer. And you stop. So it looks like a lot of extra work just to get something to be 0. Remember, you're allowed to use L'Hopital's rule whenever you want, but it doesn't mean it's the best choice. If you get infinity minus infinity, you're allowed to use it. It's not the best choice. When you get infinity divided by infinity, still allowed to use it. Not the best choice. Turns out we didn't even need it. Don't worry, we will be using L'Hopital's rule soon enough. Don't you worry, it's not going anywhere. Okay, so that is the type 1 improper integral. Let's see the type 2 type. So a type 2 improper integral is where one of the endpoints is discontinuous. So the integral from a to b, if b has a vertical asymptote, when it says discontinuous, it's talking about vertical asymptotes only. If it is a removable or jump discontinuity, you don't need to use improper integrals. This is for vertical asymptotes only. So what you do is you replace b with t. So the right endpoint has a vertical asymptote. Pull the limit to the front and say we're coming in from the left, right? The little minus sign means coming in from the left. And then the reverse is true, right? If the left endpoint is discontinuous, replace a with t, bring the limit out front and say we're approaching a from the right. Again, both of these have to exist as a finite number. And it turns out that if those limits exist, those are convergent. If the limits don't exist, it's divergent. So it's the same rule, just for different reasons, right? Earlier we saw horizontal asymptotes and behavior. Now we're seeing vertical asymptotes. And then rule C here is pretty interesting, and we're going to use this in a later problem. If f has a discontinuity at C, where C is between A and B, and both of the individual integrals are convergent, then this overall integral is the sum of the two individual integrals. So this is pretty interesting because you might be presented with a problem that looks like this, and you don't know what C is. If you don't recognize that there's a vertical asymptote in the interval and you do the integral, it'll be wrong. If you see a vertical asymptote, you have to identify it and split the problem into two pieces with two different improper integrals. Again, we're going to see one of those very soon. All right, so let's see how to use this rule. So we can see right away that this thing is discontinuous at 0. That is our left endpoint. So this is a type 2 improper integral. So we replace 0 with t, pull the limit to the front, and say we're approaching 0 from the right. I also pulled the 4 to the front and rewrote x as the minus 5 power. Do the integral. Not a tough integral, right? Take the power up 1, divide by the new power. Plug in 1 and t. Now we can plug in 0. And what's 1 divided by 0? Well, that's infinity. So this diverges. So what we've seen is that there's at least one power of x in a denominator that diverges. So it turns out some of these converge, some of them diverge for type 2 improper integrals. For type 1 improper integrals, some converge, some diverge. You will have a homework problem on that where you will find out exactly which values of x diverge for improper integrals. So I'm not going over that one. I want you to try it. It's a good problem, and you'll use it later in this class. In Chapter 11, we do stuff like that all the time. Okay, so not a bad example. Make sure you can work through these examples on your own, of course. All right, let's do another one. So what we have here, this looks like an ordinary integral that you'd see in Calc 1, right? This is a U substitution problem. You have to notice, however, that this thing is discontinuous at x equals 1. Because if you plug in 1, 1 minus 1 is 0, cube root of 0 is 0, 1 divided by 0 is a vertical asymptote. So even if I'm not telling you that's how you do the problem, from this point forward, you need to be on the lookout. Any problem that has a vertical asymptote, you have to find out if that vertical asymptote is in the interval. So go back and look at the first 3 problems we did in this PowerPoint. All of them, I at least checked that the vertical asymptote was not in the interval. So you get in the habit of checking. Because on a test, I'm not going to tell you what technique to use. You might look at this and think it's U substitution. It turns out it's an improper integral and U substitution. Right? There's a vertical asymptote at x equals 1. We need to split this integral so that the vertical asymptote is in the middle. So I went ahead and split it, 0 to 1, 1 to 9. And I rewrote the denominator as negative 1/3 power so I can do calculus. I'm going to go ahead and do both integrals at the same time. You need to split it, but if it's a substitution, it's the same one for both, so I can just go ahead and do it as one problem. Again, these are improper. So here I replace t with the limit is t minus 1 from the left. And over here, I'm just going to use s, because I already used t over here. They're technically not the same limits. Because this one's going to the right and this one's going to the left. So I'm going to call this s. You can call it whatever you want. Go ahead and do the integral. So take the power up 1, divide by the new power. Same thing here. So both of these are the same. I mean, technically it's a substitution, but you don't even need to do the substitution because there's no chain rule. So this goes from t to 0, this goes from 9 to s, and t and s both go to 1, but from different sides. So plug everything in. So all I did is just plug everything into the integral. Now I'm ready to evaluate the limit. So you just go through. Plug in 1 here. 1 to the 2/3 is 1. So this whole thing is 1. Oh, sorry. 1 minus 1 to the 2/3 is 0. This is the one that's 1. 1 minus 1 is 0. 0 to the 2/3 is 0. So this is 0. This is minus negative 1 to the 2/3. So it's just going to be minus 1. Here we have 9 minus 1 is 8. To the 2/3 is 4. And here we plug in 1. So this whole thing is 0. So everything collapses pretty nicely down to that. And you're done. So these problems chain out pretty big, but as soon as they're ready to be solved, they come back together real nice. If you go ahead and just do this integral from 0 to 9, you will not get this answer. All right, let's keep going. All right, so what we have here is a really strange looking problem. And I saved all the strange looking stuff for this problem. This is kind of what can happen if you find a wild integral in the wilderness. This is what it might look like. So this is going to illustrate a lot of the concepts we've talked about so far in this video. And it's even going to highlight even more wacky, weird stuff that can happen. So this, pay close attention because this is the type of thing you might be asked to do on a homework problem or possibly on a test. So, first thing you notice is we have some kind of divide by 0 thing going on here and the same divide by 0 thing going here. So this 0 not only is a vertical asymptote, but something else is going on here too. Because e to the infinity power, like what does that mean? Like what could possibly be going on here? And you have to remember that because we're going from -1 to 0, every number we plug in here is going to be negative. Because you might think, oh, I plug in 0, infinity divided by 0 is infinity, this is going to diverge. That's not true. If you graph this function on your calculator, on the interval -1 to 0, it looks really nice. It looks like something that will have an area. But remember, we're going to be plugging negative numbers in here. Every number we plug in here is going to be negative. So the integral itself is going to be negative. When we're done, this needs to have a negative number in front of it. All right, so that's the type of work you have to do before you even start these problems. Because some of them you can just plug in like the endpoints and say it diverges, so it probably diverges. This isn't like that. Okay, so we're going to take that 0, take it out of the integration sign and put in a limit. Now we have to figure out how to do this integral. It is not clear at all what the substitution is or anything. And you might say, well, if I do u is 1 over x, then du is -1 over x squared dx, and negative du is 1 over x squared, that this whole thing, when you plug all of this u substitution in, you just get e to the u times du, and it's negative du, so the negative is going to come to the front. Don't forget to change the limits of integration. You have to plug those into this function, so plug in -1, and then plug in t. So it simplifies to this, and then we just go ahead and do the integral. So I pulled the negative to the front. This is 1 over t. This actually stays -1. And u e to the u, when you do the integral, you get u e to the u minus e to the u. Does anybody remember how we do that? It's integration by parts, but it's not just integration by parts. It's a problem we've already done in your class notes. So if you just want to remember the answer, You're okay to do that. It's the first example we did in section 7.1 is exactly this integral. It's x e to the x. So I'm going to take this as a known integral. If you want to do the integration by parts, feel free. I already did in the class notes, so I'm going to take it as a known value. All right, so here's what I'm plugging in. So I take 1 over t and plug it in. Bam, bam, bam. Take -1 and plug it in. Bam, 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 bam. Simplify if you can. So I factored out e to the 1 over t, which leaves me with 1 over t minus 1 times e to the 1 over t. Minus, these are like e to the minus 1 is really 1 over e. So we have negative 1 over e minus 1 over e. Well, that's minus 2 over e because we have 2 of them. Again, that negative is still out front. And then you just simplify it a little bit. So all I did was this negative, negative, negative. So it's 3 negatives, so it's still negative. 2 over e. I just brought it to the front because it's not part of this limit. Right? This limit is the limit as t approaches 0. There's no t here. So I can just move anything that doesn't have a t, I can just move outside of the limit. So I just moved it to the front. Right? It was negative, negative, negative. So when you pull it out, it's still negative. But it's still minus because the rest of the stuff is still negative. And then you try to evaluate this limit. You plug in 0. And you get, now remember, it's negative. You get 1 over 0, which is negative infinity times, and then this is e to the 1 over negative infinity. So e to the minus, so it's 1 over 0, which is negative infinity. So you get a negative infinity times 0, even though it's negative 0. But it's of the form negative infinity times 0. And it turns out that if you try to use L'Hopital's rule here, it doesn't work. You get stuck in an infinite loop. So I'm sure you remember back in L'Hopital's rule, I explained what an infinite loop is. If you want to try it because you forgot what it is, go ahead and try this using L'Hopital's rule. You will see it is not nice. Instead, we're going to do another variable substitution. I'm going to say that s is 1 over t. I could have done this in the beginning of the problem, but the algebra works out better if you wait and do s later. So this limit, as t goes to 0 from the left, 1 over t minus 1 e to the 1 over t. If I replace 1 over t with s, this becomes s minus 1 e to the s. So I get this. This looks a lot nicer. So what happens when I try to evaluate that? Plug in negative infinity. I get negative infinity times 0. And you think to yourself, this is exactly what we just had. How is this better? It turns out that in this form, we are now allowed to use L'Hopital's rule. Even though it looks exactly the same, when you have this form, you don't get stuck in an infinite loop. What you do is you rewrite e to the s as 1 over e to the minus s. So I put it in the denominator and make it negative. Now I can use L'Hopital's rule on this. This becomes a 1. This becomes a negative s times e to the minus s. So there's my L'Hopital's rule symbol, little hospital symbol. And you plug in negative infinity. Negative, negative infinity is positive infinity. E to the negative, negative infinity is e to the positive infinity. Positive infinity times positive infinity is positive infinity. It's hard to say. 1 over infinity squared is 0. So it goes away. Again, a lot of work to prove that something's 0. If you can find a better way to do this problem, feel free and let me know. Maybe I'll kick you some bonus points. So far, this is the best way I've found to do it. And I had to work on this problem for, let's just say a while. What's interesting about this problem is you can do the numerical solver on your calculator because the limits of integration are from -1 to 0. So you can actually type those numbers in. So if you want to verify that this is the correct answer, you guys know how to do numerical integration on a calculator. And that's the answer, minus 2 over e. All right, one more topic, and then we'll be done with the video. And the last topic is the comparison theorem. So basically, the picture tells you everything you need to know. We are not going to prove this theorem, but it is believable. If f of x is always greater than or equal to g of x, and g of x is always greater than or equal to 0 for some number, for all numbers greater than a, then if the outside integral converges, then the inside integral also converges. And if the inside integral diverges, then the outside integral diverges. So what this is saying is, converging, think of it as being small, and diverging, think of it as being large. So smaller than small is still small, which means if you're smaller than something that converges, you converge. Larger than large is still large. So if you're bigger than something that diverges, so if g of x diverges, then f of x must also diverge. So smaller than small is small, larger than large is large. Not much as a mnemonic goes, but I think it does help in the spirit of remembering what this rule says. The challenge when you see problems like this is knowing what to compare. So you'll be given either f of x or g of x, and you have to find the other one. So let's see how to do that. Use the comparison theorem to determine whether the interval is convergent or divergent. So just looking at it, it looks absolutely horrible. You might think trig substitution or u substitution. Turns out nothing works. This integral would be absolutely awful to do. But all we want to do is determine if it converges or diverges. We don't want to know the value. So what you have to do is you have to look at it and say, do I think it converges or diverges? And then compare it to something that it's close to. So one way to do it with algebraic functions is looking at the highest power in the numerator and denominator. This is x. Okay, fine. This is the square root of x to the fourth. So it's x squared, basically. So it's like x over x squared, which is sort of like 1 over x. So if we can get this to compare it to 1 over x, if we can show that this is larger than 1 over x, and 1 over x diverges, then this diverges. If this is smaller than 1 over x, and 1 over x converges, then this will also converge. So that's what we try to do. Right? And it turns out that we can see that this is bigger than x, and this is smaller than x squared, basically. Plus or minus x squared doesn't matter. Because if it diverges, it doesn't matter if it's negative. So when the numerator is bigger and the denominator is smaller, then the entire fraction is bigger. So this entire fraction is bigger than x over x squared. And this this right side equals 1 over x. So because this is bigger than 1 over x, if we can show 1 over x diverges, then this also diverges. So that's what we're trying to do. And this is really how you have to do it. You have to like match the pieces up and think about it and then show that something converges or diverges. Now, if we happen to show that this converges, if we're larger than something that converges, it doesn't tell us anything. If we're smaller than something that diverges, it doesn't tell us anything. The theorem only works if the lower function diverges or the outer function converges. All right, so we're going to do an improper integral here. This is the most basic type, right? This is a type 1. Replace infinity with t and take the limit. T is positive, so we don't need the absolute value. So this is just ln of x. Plug in t in 1, and it diverges. And that's how you do it. So this whole thing diverges. Because the smaller function diverged, the larger function diverged as well. And that's the answer. And that's how you use the comparison theorem. So make sure you are practicing using the comparison theorem, because these are basically multiple choice questions on the homework, because it just says converges or diverges. You don't have to find any numerical answers. Make sure you are working all the way through these problems properly and correctly. All right, well, that's it. If you got any questions, let me know. And next video that you guys watch will be next week, and then you'll have spring break. But if you need anything, you can post on the discussion board, or I'll be available for Zoom meetings in the evening. So that's it for Chapter 7, and I'll see you next video. Bye-bye.